Hey guys, here we are. We're going to talk about organic chemistry and specifically quite a bit about naming things. Okay, so first off, what is organic chemistry? It's the study of carbon, essentially. Okay, so we say that we are carbon-based life forms. That means that the most critical part of our biology, of our chemical biology, is the reactions carbon can do. Carbon, as we recall, is in group 14, so it has 4 valence electrons. That means it needs to form 4 bonds in order to be happy, because everybody wants to get to 8. Carbon only has 4. So the fact that it forms 4 bonds means it very frequently has tetrahedral geometry. We remember that tetrahedral geometry is a symmetric geometry, so that means carbon tends to be non-polar most of the time, unless it happens to be attached to something like oxygen or, something crazy electronegative like that. Organic chemicals are literally all around you. Not only are you made of organic chemicals, but almost everything you touch has some component of carbon chemistry in it. For example, your backpack or the carpet at your house is made out of nylon, which is a long chain of carbons. Ethanol is the kind of alcohol that you drink in vodka and rum and beer and all of those. Your proteins are made out of carbon, among other things. Your DNA, your RNA, polyester, which is in a lot of your like business clothes. All plastic is made out of carbon. All right, so it's everywhere. So again, when we think about how carbon reacts, we want to think about the fact that it has those 4 valence electrons, so it wants to form 4 bonds. It can form 4 bonds to, other carbon molecules that's supposed to connect. Like this. Okay. Or it might form bonds to carbons and hydrogens. Okay, that's allowed. Now, one interesting thing about carbon chemistry is we can have all single bonds like this. So that would just look kind of like a chain of carbons. Or we could have double bonds. We could have double bonds. I fixed the alignment on that. Which would look something like this. Right? Or it could have triple bonds, which could be something like this. Now you can't have 2 triple bonds in a row, but you could have alternating triple bonds. That's a thing. Okay. So for each of these, you would end up attaching hydrogens to fill up the other bonding sites. So in single bonds, you can just fill them in like this. Again, 4 bonds for every single carbon. That's always going to be true. Okay. Or here we have 2 already, so I'm just going to put 2 hydrogens on this one. This already has 4. 2 here, 2 here. And then we just put 2 on the end as well. And then over here with triple bond, if this has a triple bond, it can only have 1 more bond. This one has 4 bonds already, which is what I meant when I said you can't have 2 triple bonds in a row. That would be 6 bonds, right? So that carbon can't do that. And we have a triple bond on this one, so another hydrogen. Okay, so this is just like examples. You could have kind of an unlimited arrangement of different carbon atoms, but single, double, and triple bonds are very common. What I've drawn here for you is called a backbone, right? So that's the carbon backbone. When we're building organic molecules, we always start by making the carbon backbone, and then we worry about where the hydrogens are after that. Okay, so organic chemistry is all about the hydrocarbons. So that means literally just, that there's carbon and hydrogen in it. Within that group, we have basically 2 categories. We have things we call saturated, which are also known as alkanes. That means single bonds all over the place. Nothing but single bonds everywhere. That's what saturated means. It has, all of the carbons are tetrahedral, essentially. Then we have unsaturated. That can happen if you have double bonds. That would be an alkene. Or triple bonds. That would be an alkyne. Or even a ring like this. So this is benzene right here. Benzene is like the basic unit of the aromatic category. And as you might imagine, many of the things in the aromatic category have very strong smells. So we're going to learn a little bit about each one of these categories, especially how they are named, and also how some of them react. Alright, so alkanes are where we're going to start. They're the simplest ones. They're all saturated, meaning single bonds only. Okay. The formula, this generic formula, helps us to figure out what the chemical structure is going to be. So if I have 3 carbons, that means my N here is 3. So I would write 3 carbons, and then to figure out how many H, it's going to be 2 times N, so 2 times 3, plus 2. So that's going to be 8. This is called propane, right? So I could have like a really big carbon molecule, like say 144 carbons. I just made that up for fun. And I can figure out how many hydrogens to put with it. Some biological molecules really are that big. And if it were an alkane, then this is the formula. So 144 times 2 would give us 288, plus 2 more is 290. So this would be, oops, not 190, 290. Okay. So this generic formula is provided to you on your final exam cheat sheet. It's a good way of figuring out, you know, given this many carbon, how many hydrogen do I have? Alkanes are named, and also this is on your cheat sheet if you forget, but alkanes are always named with A and E at the end. Often we have what we call branches, so it's not just a matter of having straight chains, right? So if you have a branch, it's like where some carbon thing comes off the main central chain. We have to name those in a specific way so that we know when 2 chemicals are the same thing or when they're not. Because in carbon chemistry, we can draw things in about 1,000,000 different ways and have it still be the same chemical. So learning to name is a key concept here. We start with the first 10 carbons, right? So it's very similar to what we learned about naming in the beginning of 111, where if it's nonmetals, then we just have prefixes to describe how many atoms there are. So from 5 to 10 is pretty much review. You know that pent, hex, hept, oct, non, and deca are the prefixes relevant for that. It's the same as what you learned in the beginning of 111. The first 4 are kind of particular to organic chemistry, and the more familiar you are with these names, the faster your naming process will be. So it's a really good idea to make it flashcards, at least for these 4, and maybe for these other 6, so that you are quick at recognizing how many carbons will be in each chain. So methane is our simplest alkane. It's just 1 carbon and 4 hydrogens. So you can draw it like this, and the model would look like this. Now in lab we learned about how to draw a model to show the arrangement of the atoms in space. So this doesn't do that. This looks like a flat picture. In order to show that, we're going to have this carbon in line with 2 of the hydrogens. So these are going to be just regular straight lines. And then it appears that 1 of these hydrogens is coming out at us. So that is a wedge. And then we have one that's going back into the page. That is a hash mark. Like that. Okay. It's probably better to draw it more like it actually looks. Let me just try this. Okay. So that's a tetrahedron. So we can kind of show the actual shape of a molecule using wedges and hashes. Again, this means it's coming out of the page, and this dotted line means, which we call a hash, means it's going back. Okay, so with our ethane here, we have 2 carbons and 6 hydrogens. Propane is 3 carbons and 8 hydrogens, and butane is 4 carbons. And let's see, so it's going to be C4H10. So there's 10 hydrogen on that. That's saturated. It says filled up as it can get. Okay, so these are the straight chain, meaning unbranched alkanes. They're just kind of a straight line. You'll notice in the models, they don't form a straight line. When we play with this in lab, you'll find that you can't make just a straight across carbon chain. So we draw this way to be convenient and kind of easy on the eyes. But in reality, it zigzags. Okay, so that's something to keep in mind. Now, interestingly, so the thing is that because hydrocarbons are essentially, they're nonpolar, right? Because they're symmetric. They're tetrahedral, so that means symmetric. So all of these are nonpolar, which means don't mix with water or anything else that's polar, right? So we have a word for that. Something that is afraid to be around water is called hydrophobic. Hydro meaning water, phobic meaning afraid. So hydrocarbons are hydrophobic. They don't want to hang out with water. So basically these are like oils. You can't mix oil and water. Okay. Now, we remember that things that are nonpolar have predominantly London dispersion forces, right? So those depend on size and shape. So the bigger the molecule is, the more LDF we will have, which means we are more likely to be a liquid at room temperature. So that means a relatively accessible melting point. The boiling point of these things is relatively low as well, because basically you don't have to add very much heat to separate London dispersion forces, right? And so separating from liquid to gas, which is boiling, is a very easy thing to do. So alkanes tend to be very volatile, which means that the boiling point and melting point are relatively low. They do increase as the molecule gets bigger and bigger and bigger. So like methane is a gas. Its boiling point is therefore below room temperature. Ethane is also a gas. And propane is kind of borderline. It sort of depends on pressure. Okay. Butane is mostly a liquid but quickly vaporizes at room temperature. This is what's in your like lighters, you know, your like Zippo lighters. Propane is what's in your gas grill, so obviously that's a gas, right? But inside of the compressed cylinder, it's compressed enough that the pressure is really high, so this is actually a liquid, and you can actually hear it sloshing if you shake the propane cylinder. So butane is kind of a liquid, but doesn't take very much to heat it up into a gas. The next one in the series would be pentane. That is a liquid at room temperature, but it smells really, really strongly because it is very volatile. So boiling point and melting point are going to be comparatively low, in like in comparison to water, let's say. But it increases as the size gets bigger. Also, as you get more surface area, so like the more spread out the molecule looks, the more London dispersions you're going to have. Also, another note, vapor pressure is very high for these things. And as they get larger, it decreases, of course, because you have more London dispersion forces. Okay, so it's a good idea to pause the video at this point and go ahead and name these compounds using your newfound knowledge here. So I'll wait a sec. Okay, so 4 carbons we called butane. So C4H10 is probably butane. And so you can draw it like this. And we're showing how each and every atom here is connected. So this is basically the Lewis dot structure of butane. Okay, C2H6 is going to be the 2 carbons, and then you fill in your hydrogens. You'll notice I always do the carbons first. That's a key skill, or strategy really. C9H20, ooh, that's a big one. We would call that nonane because it's got 9 carbons. So I draw the 9. 3, 4, 5, 6, 7, 8, 9. And then I'm going to fill in all the hydrogens. And I could keep doing this. I forgot to write the names down. Hang on. Butane, this is ethane. Right. So this one's nonane. I could keep filling in by drawing every single hydrogen bond, but I won't. I can also make a compressed structure, something we call a condensed structure. So I know there's going to be 3 hydrogens on the end carbons because they only have 1 bond right now. And the interior carbons are going to have 2 because they have 2 bonds right now. Quiet. So everybody gets an H2. And if you add up all these H's, they should add up to the 20, right? Okay, so it's 3 on each end, so that's 6, 8, 10, 12, 14, 16, 18, and 20. Oops, nonane is the name of this one. I didn't finish it. Here we have 1 carbon. This one's easy. It's just a carbon surrounded by hydrogens. It's the simplest one, so it's called methane. Apparently I can't cross the H because there's text things in the way, but you get the idea. So that's methane. Okay, so for the formula, that's this right here. So we can just write the formula. So hept means 7. And so it's H is going to be equal to 7 times 2 plus 2. So that's going to be H16. Hexane is 6, like hexagon. And 6 times 2 plus 2 is 14. Decane is 10. H is going to be 2 times 10 plus 2, so that's 22. And lastly, we have pentane, which is 5 carbons, like a pentagon has 5 sides. And it's going to be 5 times 2 plus 2, so 12. Okay. So we have different ways to draw structures, as I've mentioned. Sometimes we like to use kind of a compacted formula, like something like what I drew for nonane, and sometimes we like to show the entire structure, and other times we get tired of writing 100 billion carbons. So what we use is called like a line structure, and wherever you have lines that meet, that's a carbon. So here's a carbon, and also wherever you have lines that curve, come up to a point, that's a carbon. And wherever you have an end without something written, so here we've got an OH written, that's not a carbon. But over here, we have just like an end without anything written on it. That means there's a carbon. Okay. So we can also fill in all the hydrogen here because, of course, each carbon still does need to have 4 bonds. This one has 1 right now. Right? And so this zigzag happens. This has 3, so I'm going to put 1 hydrogen in here. This zigzag happens just because of the fact that carbon is tetrahedral. Okay. So there, that's our line structure. A condensed formula is a little more straightforward. You just kind of write the atoms. You're still showing how it's connected. So instead of writing C2H6, we show CH3CH3. So here, the condensed structure would be, starting from here, CH3. I'm connected to a CH, so that goes next. And then off of that CH, so a parentheses, is another CH3. Okay, so the parentheses mean this is attached to this carbon. And then we keep going with the rest of the chain. So here's a CH2, and finally an OH on the end. Okay, so that's what we call a condensed structural formula. Interestingly, carbon can be arranged in a lot of different ways. So this formula would be 1, 2, 3, 4 carbons, and 3, 4, 7, 9, 10 hydrogens, and an oxygen. So the sort of the standard formula we would have written before learning about organic chemistry is this one, C4H10O. This has a lot of different isomers. Like I could put this OH in the middle of the molecule and move this hydrogen over to the end, and that would be the same chemical formula, but it's a completely different chemical. We call those isomers. So to be an isomer, you have to have the same molecular formula, like C4H10O, but a different arrangement. So for example, C4H10 has 2 different arrangements. Quickly test yourself and see if you remember what this is called. Okay, the isomers of C4H10 look like this. So you can have one where everything is just a straight chain. This is going to have 2 hydrogen, and that's going to have 2 hydrogen, and this will have 3. Every ending has 3 hydrogen because it's only got 1 bond, right? And the middle ones have 2, so that's a good thing to remember. Another isomer would be if we take this CH3 and plop it into the middle. So now we're going to go 3 carbons, and we're going to put 1 up here. The ones on the outside all have 3 hydrogens because they only have 1 bond. And this one in the middle only has 1 more hydrogen. So our formula is still C4, H3, 6, 9, 10. So these are isomers of each other. They would have completely different names. This one is just called butane. I hope you got that right. This one, on the other hand, is going to be called a propane because there's a chain here of 3 carbons. And then we have a group hanging off. So this is going to be called 2-methyl. That's this group. And then the name of the parent chain is propane. So butane and 2-methylpropane are isomers. They have the same chemical formula, but completely different structures, which means completely different properties. And this is what makes studying organic chemistry so very, very interesting. Okay. So when we name alkanes, these are the rules we follow. I'm not going to read them all to you, but if you need to pause it and do so, go ahead and do that. I'm going to show you some examples. Okay, I think it's better to write the structure out if you can. I'm going to actually make this a bigger slide. Okay, there, I've given myself a little bit more room to write. So when I've got a condensed formula like this, I find it a little hard to name. I can't tell what the main chain is and what is a separate thing. So what I want to do is just copy this into a structural formula. And when I do this, I actually have to put my finger on the spot that I'm at while I'm writing. So I have my left hand on the screen and I'm pointing at the first carbon right here. And so I'm going to write carbon with 3 hydrogens attached to it. Okay, and then I move my finger over to the next thing and I write the carbon with 2 hydrogens attached. It's easier if I don't connect the left and right side with hydrogens because then it just allows me to write the carbon straight across. I move over one, so now I have a carbon with 2 hydrogens again. So far so good. And then I have a carbon with 3 hydrogens. So this is one molecule. Whoops. Let me just draw the 3 hydrogens separated. There. So this piece, this one molecule is this right here. And so that turns out to be, it's 4 carbons. It's a straight chain, so that's just called butane. Or sometimes N-butane, which stands for normal. It just means straight line. To differentiate it from this butane, 2-methylpropane here, which has the same formula but is not the same thing. All right, and then in this next one, I'm going to start with my finger right on the first carbon, so that's going to be this one with 3 hydrogen on it. And then that has CH2s in brackets. So this is just a condensed formula where they're not writing down every connection, right? So there's 3 CH2s here. And then we have a CH3 on the end. Okay, so this one is just a straight chain. Again, it looked weird because we have these parentheses here, but that's just a sign of someone who's lazy on their typing, right? So, or their writing. So we have 1, 2, 3, 4, 5 carbons. That is called a pentane. These are on the same slide for you, but I made them bigger so it'd be easier for you to see. So now, when I'm naming these molecules, I'm looking for the biggest chain possible. So here in our rule, we want to find the longest carbon chain. That's rule number 1. So I often number possibilities in different colors just so I can picture what's happening. So here's one where I get 6 carbons, so that's a possible arrangement. I could start down here as well. We are not confined to going left to right either, so I could make one that goes like that. That's smaller than the other one I made, so it probably isn't the one. I could make one that goes like this. Or I could have even gone 5 and 6 or 5 and 6, right? There's a lot of possibilities here. I think that the one that I started with in red might be the best one. Let's see, so 1, 2, 3, 4, 5, 6. That's 6 carbons as well. So that's a possible one. We could write that too. Okay, and then to decide which numbering system I'm going to look at, since I have 2 different options that give me 6 carbons in the chain, what I want to do is look at where the branches occur. So if I go in the purple direction, I have a branch here, and I have another branch here. So I have a branch at the 4th and 5th carbon. If, on the other hand, I chose the red one, then I would have a branch at the 2nd carbon here, 2nd carbon, and another branch at the 3rd carbon. Oops, that was the wrong branch. Let me just fix that. I like to circle the branches because it helps me to stay organized, right? Because this can get a little bit confusing. So I circle the branches so I know what is in the main chain and what is extra. The one where the branches happen at the smallest number is the one I want to choose. So that's another rule here. In this case, we have two groups that are the same thing. So these are both one carbon. We call one carbon alkanes methane. So when they become substituents, that means groups that hang off the main chain, we erase the ane part and we just make it methyl. And since I have two methyls, I'm going to say dimethyl. That's supposed to be one word. And then finally, I have to say where they occur, because they could be anywhere on this chain at all. And where they are makes it a different chemical. So I have one of them at the second carbon and one of them at the third carbon. So we're going to go 2, 3 dimethyl. And then finally, I'm finally ready to say how long my parent chain is. That's always the last thing. So 6 carbons is going to be called hex, and it's ane because it's all single bonds. Okay, so substituents get named first, and we add YL to the end. We have to say where they are with a number, and if I have two of the same kind, I say dimethyl. Now, if these two carbons were connected, it would be totally different, like if we had this situation. So still 6 carbons. If we had a CH2, CH3 coming off of this one, so this is our group, that's not a dimethyl, that's an ethyl group. That's 2 carbons attached to each other coming off of the same carbon. Okay, so be on the lookout for that. Dimethyl means 2 different groups attached to carbon. Alright, so down here we have to find the biggest chain again. So I can find 3 that way. I could go up and down. There's nothing wrong with that. I think no matter how I do it, I could even curve 1, 2, 3. However I do it is going to end up being the same like shape. So it doesn't matter. I'm going to pick the one that's vertical just for fun. So 3 carbons is called propane. So that's the ending of our word. And then I have 1 carbon hanging off here and 1 here. So again, this is going to be dimethyl. And they both come off at the second carbon. So this one is going to be 2,2-dimethyl. Got a little squish there. So this is one word. Dimethyl is one word. And I separate each number with a comma so I don't mistake it to think I mean carbon number 22. And then always our numbers are separated from the letters with a dash. Okay, this one looks fun. Try to pause the video and see if you can name this, and then double check with what I choose to do. Okay, so there's one direction that has 5 carbons. This one is complicated enough that I'm going to spend a little more time than I have been trying to identify different paths through this molecule. So there's another 5 carbon chain. If I started from the end and went straight across, that would be 5 as well, so you could do that. Let's see, what else might happen? We could go backwards. What if it was 1, 2, 3, 4? Okay, so that's going to be the same. So it doesn't seem to matter where I start or where I end. I'm going to get to the same basic place. And so I think I'm going to go with the blue one because it's the straightforward one. Just all the way across. And so let's see. I got a group there and a group there. Now if I went with the yellow one, I would have a kind of a weird group coming off, like this branched group coming off. So that makes it harder to name, so I don't think I'm going to pick that. If I go with, let's see, if I go with the, oh, I was doing blue. Oh, hang on. The red and the blue are very similar in the approach that you're going to take. So if the blue is what we're doing, then this is the one that's coming off of the second carbon. So we have a branch at the second carbon and the third carbon on the blue one. If we had the red one, we have a branch at the second carbon and the third carbon. So they're pretty much the same thing. If we went yellow, then we get this whole entire group, which would be called an isopropyl group. But it's a little strange to do it that way. So I think I'm going to stick with the blue. So since it's 5, that would be pentane. Right? And then I have, from the second carbon, I have a single carbon hanging off. So that's still called a methyl. That part. This is 2 carbons, so that'll be called an ethyl group, right? So the second carbon is methyl and the third carbon has an ethyl on it. Now, when we have multiple kinds of groups, they get listed alphabetically. So we're going to say that it's 3-ethyl, because E comes before M, 2-methyl. Or you could also see this listed as 3,2-ethyl, methyl, pentane. Okay, and then that part's the same. Those are both the same name. You can collect the numbers together if you like how it looks better, just making sure that the 3 comes first because ethyl is first, and then the 2 is next because methyl is on the second carbon. Okay, so I mentioned the isopropyl group to you. That is a thing, right? Of course, you've heard of isopropyl alcohol, which would just be this. Alcohols are OHs. Isopropyl is 3 carbons. That's where the prop part comes from. Iso means that they have 1 carbon in the center that has 2 groups coming off of it. So isobutyl would be the same thing, but with 4, right? So you've got 4 carbons here where the central one has a branch. Then this word secondary comes up. So secondary is an interesting meaning. So if this was an alcohol again, it would be called S-butanol. Here's why. So when we look at this carbon here, it is attached, so this is the one that's attached to the alcohol. It is also attached to 2 carbons, 1 there and 1 there. So secondary means 2 carbons. Tertiary means it's attached to 3 carbons. So here's our central carbon. It is attached to 3 other carbons. So tertiary means 3. So this molecule is called T-butyl. It also happens to look like a T. Okay, so if we just have an H in this spot, the carbon in the middle has 1 H and 3 methyl groups. So you could also call that like 2-methyl propanol. Well, propane actually. 2-methyl propane would be what that could be called. But it has such a characteristic shape that we often frequently just call it T-butyl because it has a shape like a T. These are common names that you probably want to be familiar with, like isopropanol is rubbing alcohol, so it's extremely common. But it would be different from, T-butyl alcohol. Okay, so when we name compounds, you want to find the longest continuous chain and then figure out the positions of things. So for example, again, here's a chain. You could number backwards. Then you would have number 4 having a group hang off. Right, number 4. You could start at the bottom and work up. It doesn't matter because you're still going to get 5. So this is going to be called pentane. And then we got to name this group, right? So this group occurs on the second one. So it's going to be 2-methyl pentane. Okay, so go ahead and finish these and write their names, making sure you find the longest chain in each case. Then, once you have those names, you have to decide if they're isomers or not. One of the first things I actually like to do before I even bother to name things is to check and see if they have the same formula. Because if 2 things don't have the same formula, they're not an isomer. And then I check and see if the names are the same. All right, so our formula is 1, 2, 3, 4, 5, 6 carbons. And 3, 6, 9, 11, 12, 14 hydrogens for this one. And so I just keep doing that, and I just make sure that they all have the same formula. If they do, then I go back and do the name. Okay? If the name is the same, they're not isomers. They are the same exact thing. Isomers have different properties, right? So go ahead and answer these. Okay, so here's another set of questions for you to work on. I'm going to name this one here, and then I want you to tackle the rest, okay? So again, each end and each kind of corner, each triangle piece is a carbon. So I'm going to put all of these in so I can visualize what's going on. I don't need to see the hydrogens, but if that helps you, then feel free to write those in as well. All right, and now I'm going to try to decide how am I going to number this thing. So if I go 1, 2, 3, 4, 5, 6. That's one way I could go. I could go 1, 2, 3, 4. So that's not very long. Maybe we go 1, 2, 3, 4, 5. So there's lots of possibilities. I think in this case, perhaps the purple one is our best bet. Oh no, maybe the black one, I think. So we'll do the black one. I could also go backwards. Like I could go 1, 2, 3, 4, 5, and 6. So that's the same length of chain. In this case, the branches would occur at the 4th carbon and the 5th carbon, as opposed to the black choice, which is 2 and 3. So I think we're going to just choose the first one we did. That's coincidence. It won't always be the first, okay? So the 6-membered chain is hexane, all single bonds, so A and E. And then I have on the 2nd carbon, I have a methyl group, and on the 3rd carbon, I have 1 carbon, so that's methyl. So we're going to have 2, 3 dimethyl hexane. Okay, so name the rest of these. Hopefully you got a good handle on it. Okay. Now here's another one where we want to interpret from the kind of condensed structure into the line structure. So we have a carbon with 3 hydrogens attached to another carbon attached to another carbon, and this carbon doesn't have any hydrogen directly attached to it, so that means we're going to have a CH3 group coming off the top and off the bottom. That's what this 2 means. And then another CH2 right here, and then another CH3. Let me just draw my other H's in here. There we go. So I would name this one, maybe if I go 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, so 5 is the best one. It doesn't matter whether I go 1 on this side or 1 on this side, because 1, 2, 3, either way, you end up with your groups at the 3rd carbon. There's 2 groups, so I'm going to number them both. They are methyls, so dimethyl. And then we said it's 5 carbons, so it's going to be a pentane. So B. And it looks like a bat. Haha. So this is the line structure of 3,3-dimethylpentane. It's very symmetric. Okay, I want you to practice interpreting these, remembering to look for the longest chain. I'm going to grade them, don't forget. Okay, so moving on. Now we have alkenes and alkynes. So now alkenes mean we have a double bond. Alkynes mean we have a triple bond. So alkenes don't have the +2 on it because we have to take away a hydrogen. So like if you have ethane like this, in order to make it a double bond, it can't have as many hydrogens, so you have to take them away, right? So basically, here's ethane. Oh, where did my line go? Just kidding. Here's ethane. And to turn it into ethene, so ENE, we have to erase the hydrogen on each carbon and turn that into a double bond. Okay, so now each carbon still has 4 bonds, but the geometry here is different. We've gone from being tetrahedral, because we had 4 individual single bonds, to having only 3 bonds. So this one is triangular, so we call it triangular planar. Okay. In the case of an alkene, you're starting with, again, let's just do ethane as the beginning, right? Everything is based on alkanes. And then we derive other materials from that. In this case, what we have to do is erase not just 1 hydrogen on each carbon, but rather we have to erase 2 because we need those electrons to be, we need those electrons to be involved with our triple bond, right? So one of the hydrogens gets kicked out and you can get that double bond, and then another hydrogen had to be kicked out to make it into a triple bond. So now these hydrogens aren't going to want to hang out together because, you know, hydrogens don't get along so well. So what actually happens is it's the end hydrogen that stays and the top and bottom hydrogen get kicked out. And so now our carbons are not triangular either. These are linear. They literally make a line when we have a triple bond. Okay, and we can show the name in a triple bond by writing YNE. That's called an alkyne. So like ethyne is this. Butene would be, so 1 butene tells us where the triple bond is, right? So 1 means on the first carbon. But means 4. So 1, 2, 3, 4. That would be butene. 2-butene is where the triple bond happens on the second carbon. So this one's very symmetric. Interesting thing about double and triple bonds is that they can be arranged differently depending on how things are, right? So here's an example. 2-butene, this would have no hydrogens right there, but this has 3 hydrogens on it, and this does too. So this is going to be like a big line, essentially, okay? For the double bond, we have 2 hydrogens on this example, but what if one of them was replaced with a carbon? And one of them on each carbon was replaced. So here we have a carbon that's on the top and a hydrogen that goes down. We have a choice here. You could put a carbon that's down and the hydrogen that's up. So this would be called trans ethene. Or we could flip them, right? And so you could have a situation where you've got carbons on the same side, like this. That is called cis ethene, right? And these have very different properties, actually, particularly important for human metabolism, okay? So anyway, here's the rules we just used. It's very, very similar to the rules for alkanes, except we have to change the ending, and we always want to make sure that the chain includes the double or triple bond. Okay, so here's an example. I want to make the number for the triple bond, well, double bond in this case, as small as possible. I could have numbered from the back here, but it's much better if the alkene part is a lower number. So we're going to number it over here. And so this one would be called 1-hexene because the first carbon has the double bond. Over here, so that's more important. It's more important to have the first carbon be the double bond than it is to have a substituent with a lower number. All right, so we could number this one from 1, 2, 3, and so that would be the third carbon, but then your double bond is occurring, you know, at the 5th carbon. So the priority is that the double bond gets the lower number. So the double bond part would still be 1-hexene, but now we got to say where this branch happens, and this branch is just 1 carbon long, and it's at the 4th thing. So it's going to be 4-methyl-1-hexene. So this one refers to where the double bond is. All right, so this one is still going to be 1-hexene at the end. And we have a branch here and another branch here. So this one is 2, that's the methyl. So we've got a 2-methyl. And over here we got 4-ethyl because it's 2 carbons, right? Here's 1, here's 1. So 4-ethyl. E goes before M, so we're going to write 4-ethyl 2-methyl. And there's a hyphen in between the 1 and the L there. So 4-ethyl 2-methyl-hexene is the name of that thing. Cool. Okay, so once again we're gonna try to name this. Never mind. No, we're not. We already did that, and the answer's on the slide. Okay, we're going to go on to the next one. So this one is an alkyne, right? So we want to try to make this the priority, right? So you can number 1, 2, 3, 4, or you could go 1, 2, 3, 4. Either way, you get to the same place. So I'm just going to pick the forward one because it's easier. All right? So that means this is the 5th carbon, 6, 7, 8. Now, if we did go backwards, I don't know, it might affect the substituent numbers. So let's just check it. Okay, so if we went with the yellow one, we would have a substituent on 2 and 6. If we go with the red one, we have 3 and 7. So actually, the yellow one is better, even though the double bond is at the same carbon, 5 in both cases. The yellow one gets the priority because the substituents are lower. Okay, so we got to check both of those just to make sure we're right. 8 carbons is always called oct. right? And normally if it was 8 carbons, all single bonds, we'd call it octane, but this is a triple bond, so we're going to say octyne. And we got to say where that triple bond is. So it's at the 4th carbon. Wait. Oh, yeah, 4th carbon, that's right. All right, and so then we also have a group here and here. All right, so our substituents are both methyls. So I'm going to do the dimethyl thing again. And the numbers are 2 and 6. So it's going to be 2,6-dimethyl -4 octyne. It's not a choice. I think we're smarter than the example. This one was probably the one they wanted us to pick, but we noticed that you get the same number for the triple bond, and the substituents are lower, so we tricked them. This is a better answer. Ooh, oh, that's a terrible box. Anyway, the best answer is 2,6-dimethyl 4-octyne. Okay, so you're going to have a chart kind of like this in your final exam pamphlet. You should get used to using it, right? So these names are here to help you remember what they're called. So alkane, ene, and yne tell you what the ending of the chemical will be. Here's the general formula we've used. And in this case, they have sort of a skeleton structure. I think in the actual packet, you have examples instead, but it's kind of the same idea. And then we have cycles that don't have any double bonds in it. We call them cycloalkane. So like this one here is 1, 2, 3, 4, 5, 6 carbons. So we would call that cyclohexane, because 6. And down here we have aromatic things. This is benzene. So other ways to draw this show the double bonds. There's 3 of them specifically. But because those double bonds have resonance structure, which means they move around in the Lewis dot structure. So all of these things exist at the same time. So that means those double bond electrons are shared. So we just draw this circle that's supposed to mean 3 double bonds. Okay, so that's what benzene looks like. We call those the aromatic hydrocarbons. Okay, so here's how they react. Okay, so we know about combustion. You can burn every single hydrocarbon ever invented. Okay, that's because they're very volatile. Remember, low intermolecular forces, so they're very volatile, which means they are flammable. When they burn, they produce a lot of energy. We use these for things like natural gas for heating our houses, propane for running stoves and barbecues, octane for running your car, that's gasoline, or at least mostly. Jet fuel, like anything you can think of that is a fuel is a hydrocarbon. Hydrocarbons combust with oxygen. You can never have combustion without oxygen. So in other words, sorry, no barbecues in space. When you combust a hydrocarbon, it's going to produce CO2 and water. Okay. Alkanes react like this the fastest. So this is pretty much the only reaction alkanes can do because they are saturated. There's no other reactivity for alkanes. So for example, oops, too low. We have, say, methane. It is going to combust with oxygen to produce CO2 and H2O. This is always the format, no matter which hydrocarbon you put in here. We just got to balance it though. So I need to have 4 hydrogen on the left. I got 4 on the right now. And on the right, I have 2 oxygen there and 2 oxygen here, so I got to have a coefficient of 2 there. So now it's balanced. Okay, so that's review from 111. We've seen a bunch of combustion reactions. Okay, but that's all alkanes do. They don't have any other reactivity that we're going to study. Things with double bonds or even triple bonds can do some pretty cool reactions. One of which is called addition. Addition reactions are the way that we get hydrogenation. So hydrogenated fats are things like margarine, right? Margarine starts out as an oil and you pump a bunch of hydrogen in it. And so being an oil means it's unsaturated. You got double bonds in there. So this is just a fragment of the oil. And when you put in hydrogen gas, it's going to react in this kind of neat way where one of the hydrogens connects to one of the carbons and the other hydrogen connects to the other carbon. So basically they are going to break this bond up. And so what you get is an alkene becoming an alkane, right? So we break the double bond. You can break it with hydrogen or anything that's diatomic. So let's say I have just some ethane here, or sorry, ethene, right? It's a double bond. And if I add hydrobromic acid, actually I'm going to draw them in different colors. So the bromine's going to be blue, and I guess we'll make the hydrogen red, just to make it really clear what's happening. Hydrogen's going to go to one of the carbons and steal the electron that was involved in the bond, and bromine is going to go to the other carbon and steal that electron. And so what we're going to get is bromine connected to the carbon and the hydrogen on the other carbon connected to that. Oops, that's wrong. Hang on. So two carbons here. One is bromine, and on the other one is going to be a hydrogen. Okay, so basically we break the double bond and put one of each atom on the carbons. And those hydrogens are still here. So it'll go from an alkene to an alkane. All right. When we do with hydrogen, it's called hydrogenation. When we do it with anything else, it's just an addition reaction. We are adding to the double bond. So we break the double bond and we add atoms to each carbon that had a double bond in it. Okay. I'm going to clear up some space so we can look at the substitution. Okay, so in a substitution, we are talking about benzene, which has 6 carbons in a ring. And that means, so each carbon has one single bond and one double bond. So that's 3. So each one of them also has a hydrogen sticking off of it. Now, if I take like bromine, Br2, or H2, well, not H2, let's say HBr, okay? If I take HBr, what's going to happen is the bromine is going to attack that carbon and take the place of one of the hydrogens. So here's our bromine. It's going to go in and attack this carbon. That means this hydrogen has to leave because the carbon double bond and single bond in the ring are too strong to break. So what we end up with, I'm going to draw it down here, is we have our carbon ring still with our double bonds, and we have taken off an H and put on a bromine. And this H is actually going to pair up with the other H, so we're going to get bubbles. We're going to get hydrogen gas out of that. That's called a substitution. So one of the H's on the ring gets kicked out and the bromine takes its spot. So obviously, you know, we're substituting. We're not breaking any double bonds or the ring, okay, because that is a really, really strong arrangement. Okay, so here's another example. We take an ethene and we add bromine. Okay, so we did this in the lab, right? So we add Br2 as a way to test and see if something has unsaturation in it. If it does have unsaturation, meaning double or triple bonds, then one of the bonds is going to break and bromine gets added to both sides. So this orange color, this is bromine, which is orange, goes away and it becomes just a colorless solution. You can do the same thing with any carbon-containing compound that has a double or triple bond using hydrogen. So this is hydrogenation. Okay, and what you get out of that is the alkane. Now, sometimes when you hydrogenate things, unexpected stuff happens. Okay, so ideally, if it were a perfect reaction, you would get a straight chain alkane from it, and everybody would be happy. This would be a fat, a solid fat. This is an oil because it's unsaturated here. Okay, so a solid fat would have a straight chain geometry like this, where every carbon is tetrahedral. However, when you do hydrogenation, there's this little side effect thing that happens. This is a cis isomer, cis meaning together, so the carbons are on the same side, cis being together, right? So the carbons make like a little trapezoid shape there. when you hydrogenate something, a certain percentage of your carbon chain turns into trans. So trans means across. Like transatlantic flight means to fly across the Atlantic Ocean, right? So this would be a trans fat, and trans fats are not good for you. They cause, we think they cause heart disease. They build up in the blood vessel because they have sort of a bigger shape. Cis isomers can stack together pretty well. You just keep stacking them like this, like cups, basically, right? You keep stacking them. Trans isomers are hard to stack because of this shape here being kind of like a wiggle. So getting them to stack together is very difficult, which means trans fats have a tendency to form big clumps. Okay, so don't eat them. All right, so moving on. Benzene is the basis for aromatic compounds. Okay. I think I'm going to cut this video off here because we're getting a little lengthy, but so far we've covered naming and chemical reactions of all the basic hydrocarbons, and then we're going to go into aromatics after this. Stay tuned.